Hi, and welcome to the tutorial series on how to build your first DirectX 12 application in C++. During our last episode, we implemented our planar shadows and got rendering up and running for that. That means that now we have a system with materials, we have lighting, we have shadows, but we do not have any system that can handle simulations, which is usually something that you want to do in terms of DirectX 12 applications. Most of them do some sort of real-time stuff, and you might want access to a so-called timestep. A timestep is basically a clock that tells you how long time passed since your last update call. So let's do that. We will create a system here. Oh, that is probably why. Okay, I actually uploaded the system itself, but the application probably doesn't have a system. Okay, and that's because I had to redo some episodes. So let me just show you what I implemented. Usually I don't do things like this, but since this is a redo of a previous episode because of some problems, let me just show you. The timestep is a class that we export to our API, and it has a constructor and it has a tick function. It stores a time point internally that it updates. And the actual implementation is once we create a timestep class, we set the clock to the internal clock to whenever it was created. Whenever we call tick, we store the last time recorded in a temporary. We update the current time stored in the class, and then we compare, or rather calculate the differences, and then we count the amount of seconds that or I think it's microseconds that went on since the last call to tick, or since the object was created. So in our application here, we will include a timestep, which we will create. Let's see, timer, timestep, timestep system, and it will immediately be initialized whenever we create it. But in our application here, we want to be able to actually set it. So we will tell the system to tick every frame, and we will also store it as a variable called timestep. We would like to pass this to our renderer. So let's change this to take a constant float timestep, and we simply pass it along into our update draw method here. So now our renderer actually knows how long time passed since our previous timestep. Okay. We would like to be able to do computations for our different components. For instance, if we wanted to animate a light that travels what do you call it? Maybe we want a traveling light that is somewhat like a sun that goes from the east to the west. We could create a simple animation here. That would take a float. Let's say that we want a light cycle that starts at midday, and this ranges from 0.0 to 1.1, so it's normalized here. We will set our lights to be directly at midday here, so that our computations fit our initial state. And then we will do some calculations here. We want to, let's do a separate area, simulation. And we want something like an increment here that we calculate by a value that we multiply by our time step. And then if our light cycle here is equal to or greater than our maximum here, we reset it. And afterwards we increment it by our increment value. This means that each frame we update our light cycle and we wrap it to the interval 0, 0 to 1. That will give an indication on where we are in the life cycle of, or rather the light cycle of this animation, meaning that we know if we are at east or west. Since the rotation of the sun is, we will handle it by a call to the so-called XM matrix rotation around a normalized axis. Takes in radians, and since we start at midday, we know that our rotation will be either, if we do only the day part, our rotation will be limited to 180 degrees, meaning that the 0 point is equal to the sun is rising in, well, I need to make sure that I don't mess this up. It's rising in the east, of course, meaning that it would rise over here if we expect us to be aligned with the compass, with a north forward being the north direction. So since we're starting at midday, east would be one part of the actual rotation, and west would be the opposite part of the rotation in terms of the angle. Again, we're starting at midday. So since we would need positive and negative angles, let's create a so-called clamped cycle that is equal to our light cycle times 2 minus 1. This will set it between -1 and 1, with 0, 0 being midday. We also want some sort of max rotation in the endpoints of this cycle here. Let's do maybe the half of pi as a max rotation, and let's convert that into an actual rotation, where we take our max rotation and use our clamped cycle here to calculate how much we rotate. And then we want to use this method here to create a matrix that we can multiply our light vector with to get the actual rotation. So we need to store a matrix here, rotation matrix, which we will then create from the XM matrix rotation normal. And we will pass in the axis that we will rotate around. We will rotate around the axis that the sun will rotate around. From our viewpoint here, it will be our north-south axis, which means the z-axis. And we pass in the actual rotation here, and we calculate the rotation. Since this is a simulation that happens every frame, we calculate the new position of our lights every frame. If we were to save this new position, when we of course multiply the light vector direction vector with this, we would get an increasing amount of rotation, and we would get a lot of flickering. So we want to calculate something that is our actual or frame-based light direction. Let's see, it will of course frame light direction, which will initially, no, which we will simply calculate directly here. We will transform this vector 3 by, first we need to load it of course as a lights vector here, or rather a vectorized component. So we access our light direction here, and then we want to pass in our rotation matrix. Rotation matrix. And this is our frame-based light direction. We want to store this in a well, now we actually want to update the position here inside the shaders, because our light position will have changed, but we don't want to overwrite this. So we actually need a sort of light structure here current frame lights, which we will initialize as our current light, but we will update the direction here by storing our newly created load here. Okay, we actually just call that. Let's see, our current frame lights direction, of course a reference, and then we pass in the frame light direction here, vector, and we just delete this. That also means that we will not be copying this anymore. We will be copying this. Also, we will not be using this light direction for the shadows. We will be using this. And this should actually be quite all right. Let's see, we have a problem somewhere. Oh, let's see, maybe I need to, okay. Maybe I need to add them to the project again, because it doesn't find them. It's due to some linker error. Let's see if I look at the local branch here inside our source code system timers. We do have the files. Can I add them, exclude from project? We're in a let's see. And how do I add it to the GitHub stuff so that it, well, right now it's not included in the project, so at least on the version that we have here. Let's see, maybe if I open and close the project. Let me just see. Whoops, that's opening in the wrong IDE. Okay, now it registers that this has not been included. Let's see, does our change still appear? Yeah, everything looks fine. Let's include it in the project here. And let's see if everything builds. As you can see, we now have animated shadows. And maybe we wanted to create some longer cycle. I don't know how the lighting is handled when the sun actually is below the plane here. Let's see. That will be interesting. Well, nothing happens. We have darkness. And sometime soon we will have some shadows here. Okay, we have a full day-night life cycle. And of course, shadows move a lot more during the last parts of the day, where the angle between our objects kind of like get kind of parallel, at least in terms of projecting the vertices on the plane. Anyway, I think this was a nice little bite-sized episode episode on how to do a bit of simple simulation and animation. Our scene here looks quite nicely. You could of course do improvements to the toon shader. Usually people do some more interesting shadow calculations on the actual faces of the objects. Yeah. You would basically write a more interesting pixel shader for your faces here. I see people sampling translating this value here into a gradient, which kind of like maps to either light or dark. Yeah. But I guess you could play around with, yeah, however you'd like your shaders. All right. I think that was it for this whole series. Um, I hope you liked it and learned something from it. It was nice for me to do, even though the shadow computations were something that I had to understand. I haven't done shadows as planar shadows before, so that was definitely a learning experience for me. But yeah, I think this project turned out quite nicely. It of course had to be limited in scope for us to be able to do something with it and have an achievable goal. As mentioned during the series here, if you have any specific requests in terms of tutorials, um, you are free to uh, request them especially in the comment section down below. But for me to do another video series on a certain topic and creating a tutorial on different stuff, there would need to be a fairly large audience for that, and you might not realize that sometimes the scope of things that you request for the tutorial series might be fairly extensive, so that will also be somewhat of a limitation to our whatever I'll do here in this series. Of course, I'll do more advanced stuff on my regular live streaming series. I will implement shadow mapping and probably some physics-based rendering and bloom effects and other different stuff on the live stream, but it's not a tutorial series. It's more of a live coding series, and I might even do offline work if I'm trying to really focus. But yeah, at least some topics will be discussed there, and you can always join the stream, hang out, ask questions, and interact if you want to. So let's call it a wrap on this video series. Thank you for dropping by, and as I've mentioned, feel free to interact with the content and subscribe. Also, if you find any of my work helpful, feel free to support the channel. You'll know how if you check out the description. All right. Stay strong, stay healthy, and thank you very much. Bye-bye.